let's talk about kernel heap and how slab allocators work. Now, we've spent a lot of time talking about the heap in prior modules, right? But everything we've talked about has been specific to userland heap. And beyond that, it's been specific to glibc's implementation of a userland heap. Now, that is the common case for a lot of Linux systems, so it makes sense to talk about this. Right? We had a whole module dedicated to Tcache, which is like the performance optimization caching layer that a lot of dynamic memory requests can be satisfied via. And so it's definitely worth talking about and exploring how that works. Now, if something can't be satisfied by the Tcache, it goes into kind of the greater heap. And that's where we have to deal with kind of this concept of bins. And we have the unsorted bin, we have the large bins, the small bins, the fast bins. And we see that free chunks kind of move between these different bins depending upon what's going on in as far as dynamic memory that is available and what is being requested in dynamic memory. But the Linux kernel uses a completely different implementation. And one of the questions that, I certainly asked is why? Why does the Linux kernel need an entirely different heap? Well, let's think about how the kernel works and kind of the unique constraints of the kernel. So above all, the kernel cares about performance. And userland cares about performance as well, but there's a very different impact of a slow path in userland versus a slow path in the kernel. If I write some slow userland program, the only thing that's slow is my userland program. Now, if the kernel has a slow code path, that slows down every program on the system. And the reason for that is because every program relies on the kernel to get any type of real work done. Now let's think about some of the operations or actions that occur inside the userland glibc heap implementation. Well, the userland heap spends a decent amount of time reading and writing metadata, like previous size or the size, next pointers, previous pointers. For large bins, there's additional pointers to try and navigate the free chunks that are being tracked by the heap. And on the topic of these free chunks, the glibc implementation of the heap spends a decent amount of time moving free chunks between all of these different bins. I may have something in the unsorted bin that then needs to go to the large bin, right? And that is additional work that needs to occur. It's additional cycles that are occurring in order to kind of do that accounting or track that. Or what happens if I try and malloc something, and there is a free chunk that is large enough, but it's a little bit too large? Well, the glibc heap implementation may break that chunk in two, and then have to sort the second half of the original chunk. Again, that's more work that is being done that maybe a different implementation of the heap could otherwise avoid. Additionally, the kernel essentially runs forever because the kernel runs as long as the system is up. It isn't like a userland program where we can start it up, stop it, and then restart it. Restarting the kernel is essentially rebooting your computer. And so the kernel has to be memory efficient. It can't lose track of memory or have memory leaks. Now, we already talked about the additional memory that's kind of used, potentially, from storing metadata in the userland heap representation. Well, if we can avoid that, that is a space savings. The additional thing that we can do is something that we didn't really talk about in detail, talking about the userland heap, but the glibc heap implementation is susceptible to memory fragmentation. Well, what do I mean when I say memory fragmentation? Well, let's consider the 3 lines of code on the right-hand side of this slide. We malloc hex 80 bytes. We then free those hex 80 bytes. Then we malloc hex 60 bytes. Now, let's ignore the Tcache for right now and just think about what goes on kind of deeper into the heap. Because this is a contrived example, and so we're going to ignore Tcache here. Well, there's a reasonable chance that the second malloc of hex 60 bytes will be satisfied by the free chunk that we just freed in the line above. Now, by doing so, we take the larger chunk and we break it into two pieces, and we return the allocation of hex 60, and we'll end up with a unused chunk of size hex 20. Now, if I were to repeat this operation here, these three lines of code, throw it in a while loop or in a for loop, and run it several times, what we would see is every iteration of this is creating one of these hex 20 chunks that the code isn't using. At no point does the code that is actually running need or use this hex 20 size chunk. And so we're creating all of these hex 20 size chunks that serve no purpose. Now, this is a contrived example, obviously, that you wouldn't want to run this, in an infinite loop. However, from the kernel's perspective, it's totally plausible for this series of allocations and frees to occur. And the kernel needs to run indefinitely. So these little kind of unused chunks that get created from this pattern would build up over time and result in fragmented memory that is essentially useless. And that is certainly something that the kernel wants to avoid. The Linux kernel's heap implementation relies on something that's known as a slab allocator. Now, the term slab is overloaded within this domain. So there are two usages of the word slab. Slab, if it is lowercase, implies a contiguous region of memory, a slab of memory, or a slab allocator, an allocator that uses this concept of slabs. However, if the word slab is all capitalized, this refers to a specific implementation of a generic slab allocator. Now, there's three different implementations of slab allocators that have been used in Linux. The first is Slab, which is an acronym for a simple list of blocks. I list this as deprecated. However, it does still see some use in memory-constrained environments. So like on embedded systems, there may be a Slab implementation of a slab allocator. There is also the Slab implementation of a slab allocator. This is where that kind of redundant use of the word slab can get a little confusing. The Linux source code does allow for compiling with this slab implementation. However, it is no longer the default and hasn't been for quite some time. The default kind of Linux kernel implementation of a slab allocator is known as SLUB, which is an acronym for an unqueued slab allocator, right? And so everything past this slide will be referring to the SLUB implementation of a slab allocator. The kernel's heap implementation differs quite a bit from what we've seen in userland with glibc's heap implementation. And since the implementation is quite different, we have different terminology that is used. It would be technically incorrect to refer to chunks when talking about a slab allocator. So the terms that we're going to kind of be throwing around here, first is cache. Now, a cache is kind of the highest level concept when we're talking about these allocators. A cache is created for a specific size. So there's many different caches that are used within the kernel's allocator. There's a cache for 256 byte objects. There's a cache for 512 byte objects. If there is some specific size that needs to be managed by the heap, a cache is created specific to that size. Now, caches manage something called slabs, and this is where the generic term of slab allocator comes from. A slab is a contiguous region of memory that can be one or more pages in size. It kind of depends on what is being managed as far as how large is a slab. And these slabs consist of a series of slots, where the slot is a region of memory. Within the slab,
that is the size being managed by the cache. So if we have a 256 byte cache, then the slots that are on the slab will be 256 bytes in size. Now, slots can contain objects. So if the slot is the region of memory that is 256 bytes in size, what happens when a malloc occurs, or a k-malloc in the case of the kernel, is the pointer that is returned is a pointer to one of these available slots. And once that available slot is being used, we would say that that slot contains an object or a kernel object. And so we see here that a pointer that was returned from calling k-malloc or somehow getting an allocation would be a pointer into the region of memory of the slab, and specifically pointing to a slot that now contains an object. Now, one of the kind of benefits of using this slab allocator approach is that once objects are initialized, that initialized data can be reused when possible. So if we think about how the kind of glibc heap implementation worked, if we called malloc and then free and then malloc again, we have no guarantee about the values of the memory that is returned to us. However, with this slab implementation, if a cache is created for a specific object type, for a specific data structure, and there are kind of static values, then once all of the slots have been initialized with that static value, we can assume that that data is already there when we obtain the allocation, because the only thing that these regions of memory are being used for are those specific data structures. So the diagram on the right is more conceptual than it is technical. A more technically accurate representation of the kernel heap implementation is shown here, where we are specifically calling out the actual data structures that are used. So the highest level data structure is the kmem cache. And so there's a kmem cache for 256 byte objects. There's a kmem cache for 512 byte objects, right? And so the kmem cache is conceptually the same thing as our cache. However, in the cache's implementation, it uses these two other data structures. It has the kmem cache CPU, and it has this kmem cache node. Now, we can think about this split here as follows. The data structures on the left here are represented to kind of the working set or the working slab that is in use for a specific CPU. Where the data structures on the right here contain information about slabs that are not being used by the current CPU. So why do we have this kind of division? Well, this is very similar to what we have with tcache in the glibc heap, right? Tcache represented thread local storage. There are allocations that the thread can obtain without having to kind of block and wait for the greater heap. If there are multiple threads that are trying to malloc something, we don't want to have all of these threads waiting on each other. It's a similar idea here with the kernel heap implementation. Except instead of locking on a thread, we are on a CPU-specific kind of reservation level. So the data structures on the left-hand side are what the current CPU has reserved, and it can access and allocate from without worrying about having contention with other CPUs. So for every cache, for every CPU, there's an active working slab, right? There's this working set that the CPU is interacting with. That's what we see here in green. But when a new slab is needed, partial slabs can be swapped in, right? So like if we consider we have this working set over here on the left-hand side, what happens when all of the slots are full and we need to allocate another object? Well, the kmem cache can go over to the right-hand side, find a slab that has open slots, right? It may have some slots allocated, but it should have some open or free slots, and it can kind of claim ownership of that slab or that region of memory as its new working set that it is going to use. Now, partial slabs are tracked in a linked list. They are in this NR partial pointer in the kmem cache node. Full slabs actually aren't tracked at all unless the kernel is compiled specifically to do so. So when we fully allocate a kind of backing region of memory, the kernel can just forget about it because the kernel trusts that kernel code will manage that properly. At some point, it will be freed, and when it is freed is when it needs to be tracked again. And so if we have a slab that is fully allocated, we don't even know where it is. The kernel doesn't care. But as soon as one of those objects are freed, it becomes a partially allocated slab. It's a partial slab. And it is at the time of when the first object is freed that slab will be added to the metadata over on the right-hand side, because suddenly it at least has one slot, and so it could be used in a working set. So there are no tracking of full slabs unless it's explicitly compiled to do so. Now, that was a lot of components to show in a single slide, but fortunately for the challenges and kind of concepts that we're exploring in this module, we really only need to focus on the memory that is backing the slab, as well as the slots that exist within that region of memory. What we're primarily going to be looking at is how the objects are allocated on the slab in those slots and how those slots relate to each other. So focusing on the slab's memory, we can think of this as a contiguous region of memory that's made up of fixed size slots that are either free and available for allocation, or the slot currently contains some kernel object of that size. Recall that all slots on a slab are a fixed size because that slab is supporting a specific cache, and everything from one cache has a fixed size. No space is wasted on metadata for allocated objects. So what happens when we free an object? Well, very similar to Tcache, freed objects are pushed onto a singly linked list. For the slub implementation of the slab allocator, this free list is a singly linked list, very similar to what we see in Tcache. So here there is one slot on the free list, and the next pointer is null. So what would happen if we were to free this fourth slot, which currently contains a kernel object? Well, we would do the same thing that we normally do when we're talking about singly linked lists. We would push this onto the head of the free list and then update the next pointer. And that's exactly what happens. If we were to free this fourth slot, the free list head pointer now points to the fourth slot, and a next pointer is placed inside the fourth slot that points to the third slot. And then the next pointer of the third slot is null, indicating the end of the linked list. If we were to then allocate an object, we would simply pull from the head of the free list, and that would return the fourth slot where we would place that kernel object. We would update the head of the free list to be head next, and so the head of the free list returns to become that third slot. One important difference to be aware of when thinking about this linked list is the location of the next pointer. When we took a look at Tcache's singly linked list, the next pointers were located at the beginning of the freed allocation. With the kernel heap, the next pointer is located midway through the freed slot. So in this example, we're working with slots of size hex 100 bytes, or 256 bytes. So the next pointer would be offset 128 bytes, or hex 80 bytes, from the beginning of the free slot. This is done to hopefully prevent the scenario where a small out-of-bounds write would corrupt the next pointer. Caches can be created via the kmem cache create function. Now, you may want to create a dedicated cache for a kernel object, because you know you're going to suddenly be needing to allocate a large number of these objects, and you want to have certain performance characteristics. And so you'll find more reliability by having a dedicated cache for that specific kernel object size. It can also be used to isolate those objects from the objects that are found on the general purpose cache. Now, in order to allocate from a specific cache, you use the kmem_cache alloc function. This allows you to specify the cache from which you are obtaining an object from. Since caches have a known size, you actually do not specify the size of the object you are trying to obtain because it's already defined by the cache itself. The common case, however, is to use kmalloc, which is used for general kernel allocations. And if we look at the function signature here, kmalloc is very similar to userland malloc. Kmalloc takes a size as well as a flags parameter. Now what kmalloc does is it will use the general purpose caches and it will choose which one is appropriate based upon the requested size. Now these general purpose caches have a naming convention such as kmalloc-8k, where 8k is the size of the slot that is offered by that cache. So there is a kmalloc 256, there's a kmalloc 512, there's a kmalloc for a large number of slot sizes. And when you call kmalloc in the general sense here, it's going to use one of these general purpose caches to fulfill that allocation request. Now, one of the more recent additions is the addition of the GFP kernel account flag. This is used specifically to note that the allocation is going to be some kernel object that isn't necessarily trusted. Like, say it's some kernel object that also contains userland data, right? We're going to copy userland data into this kernel object. By specifying GFP kernel account, these allocations will go to a dedicated cache that kind of mirrors the general purpose kmalloc caches. So instead of going to, for instance, kmalloc-8k, it would go to a cache named kmalloc-cg-8k. And this is where these untrusted allocations can reside. This is, again, to further separate concerns. Data that is purely in the kernel can go in the general purpose caches, and data that may be influenced by factors outside of the kernel can go to this kmalloc-cg series of caches.
To wrap up, let's take a look at some of the caches that are available on the Dojo system. So over here, I am already SSH'd into the Dojo, and I have already ran the VM connect command, so I am inside a VM on my challenge instance. If I were to run the command sudo cat proc slab info, we should see quite a bit of output here, and we do. If we go up to the beginning of it, what we'll see here is slab info version 2.1. We then have some header information. So let's take a look and see what this output is. The first column is the name of the cache. And so we see that there are caches that are named after specific kernel objects, right? We have, for instance, this kheap object or this IP6 frags object. So there are definitely objects that have dedicated caches. And if we were to scroll down closer to the bottom of this output, we will see here are the general purpose caches. So we have, for instance, that kmalloc-8k or kmalloc-256, kmalloc-96. These are general purpose caches that are used for kmalloc. If it's just like a general allocation, we aren't specifying a specific cache. It's going to use one of these kind of generic ones. Now, I said if we use the GFP account flag, then kmalloc will use one of these caches here, where it's kmalloc-cg and then a size. And we see these caches also exist on this system. And if we go back up to the top, let's check the header data. We get to see the number of objects that exist within that cache, the size of the object, as well as number of objects per slab and pages per slab. Because recall, a slab is not necessarily equal to a page, right? A slab can have a backing region of memory that is multiple pages. And we see that is the case here on this second cache for this 9p fcall cache. It looks like the objects that are returned from this cache are quite large in size, about 131,000 bytes. And so there's one object per slab, and a slab is 64 pages for this particular cache. I have no idea what this kernel object is that the cache is meant to support, but it's clearly quite large. If we look over to the far right of the header data, it looks like this does wrap around. The other piece of information that I find quite interesting is the number of slabs. So this is going to be the second to the end value here. And so we see right now there's some caches that actually have 0 slabs, right? They have zero objects, and in turn they have zero slabs, which makes some sense, right? Why keep the slab around if it doesn't need to be used for anything? And we can scroll down here and we see, well, there are some caches that have more than one slab. This NFS read data, for instance, it is 2 pages per slab, and it has 4 slabs. So that means that there's 8 pages backing the data of this NFS read data cache. It has 36 objects of 896 bytes in size. And so this is, very interesting, and this is an easy way to kind of see these caches on your system.